Determine whether an ordered pair is a solution to a system of linear equations. When two or more linear equations are grouped together, they form a system of linear equations. Here is an example of a system of linear equations. They're both in the form ax plus by equals c, which is the standard form of a linear equation. The solution of a system of linear equations are the values of the variables that make all the equations true. A solution of a system of two linear equations with two variables is represented by an ordered pair with an x value and a y value. Let's look at an example where we are going to determine whether the ordered pair -1, 5 is a solution of the system of equations given here. So first, we want to see if this is a solution to the top equation. And it's 3 times -1, which is the x value, plus 4 times 5, which is the y value, is equal to 17. So simplify the left-hand side. First, we're going to do the multiplications. So 3 times -1 is -3, and 4 times 5 is 20. And then we're just going to combine these terms. -3 plus 20 gives me 17. So it works in the first equation. So now we're going to look at the second equation, and we're going to plug in x and y. X is going to be -1, y is going to be 5. So now we're going to do that arithmetic on the left side there. The multiplication, -5 times 5 gives me -25. And then I subtract and I get -26 equals -7, which is not true. So while this ordered pair is a solution to the top equation, it's not a solution to the bottom equation. Therefore, this ordered pair is not a solution to the system of equations, because it would have to be a solution to both equations. All right, let's take a look at this second ordered pair. So we have determine whether this ordered pair now is a solution to the system of equations. So we're going to plug it into the first equation. And when we plug it in, we get 3 times 3, which is 9, plus 4 times 2, which is going to be 8. So 9 plus 8 is 17 is true, because 9 plus 8 is 17. So it works in the top equation. Plugging in 3, 2 in for x and y gives me 17 is equal to 17, a true statement. So now I'm going to try it in the second equation. Remember, before it worked in the first, but not in the second. In order for it to be a solution to the system, it has to work in both. So I'm going to plug in 3, 2 for x and y here. And it's going to be -5 times 2 is -10. 3 minus 10 is -7. So -7 equals -7. It also works in the second equation. So here we have an ordered pair that is a solution to all the equations in this system of equations. This is a solution of the system of equations. So this is how you can verify that an ordered pair is a solution to a system. But how would you actually find the solution if you were just given the system? Here is one way we can solve a system of linear equations by graphing. Here's the system of linear equations here, and we're going to try to solve it by graphing. So in order to graph it, I'm going to put both equations in slope-intercept form. So here, 3x plus 4y equals 17, this top equation. I'm going to solve it by subtracting 3x from both sides. I'm solving for y to put it in slope-intercept form. That's going to give me 4y equals -3x plus 17. And then I'm going to divide both sides of the equation by 4. On the right side, I just divide each individual term by 4. On the left, the 4's will cancel, leaving me just y, so it's now in slope-intercept form. Negative over positive gives you -3/4 of x plus 17 over 4. So we're going to graph the y-intercept. The y-intercept, if x is 0, the y value is going to be 17 over 4. 17 over 4 is a little bit more than 4. It's like 4 1/4. So I go up to about 4 1/4, and I'm going to put a dot here at 4 1/4. And then from here, I'm going to follow this slope, rise 3, -3 actually, and run +4. So I'm going to rise -3, which means go down 1, 2, 3, and I'm going to run +4. 1, 2, 3, 4. So I'm going to have another point here. There's going to be another point. And then when I connect those dots, that's the line we're talking about. Okay, so that's the first line. Now let's draw the second line. So we'll first have the equation put into slope-intercept form by subtracting x from both sides, because we're trying to isolate y. So we subtract x from both sides, and that's going to give me -5y equals -7, or -x minus 7. And then I'm going to divide both sides by -5. So the left side, the -5s are just going to cancel. On the right side, I divide each term by -5. A negative divided by negative makes +1/5 x. A negative divided by negative makes +7/5. So I'm going to graph this one also. 7/5 is a little bit more than 1. It's 1 2/5. It's almost actually 1 1/2. So I'm going to go up to the y-axis between 1 and 2. I'm going to make the y-intercept there. And then from there, I'm going to rise 1 and run 5. So I'm going up 1 and over 1, 2, 3, 4, 5. And here's where my other point is. And I graph that point. And then when I connect those dots, I'm going to get the graph of this second line. And when I look at where those two lines intersect each other, right there, it is the point 1, 2, 3, 1, 2, the same point that we checked already and saw was a solution to this system of equations. So one way of figuring out what the solution to a system of equations is to just graph the equations and figure out where the two lines intersect each other. That intersection point will be the solution. Let's take a look at another example. Let's take a look at this one, solving this system by graphing. So first I'm going to put both equations in slope-intercept form. I'm going to do that for the first equation first, so let's do that. We'll have this one, we'll solve for y to put it in slope-intercept form by subtracting 5x from both sides first. When we subtract 5x, we get -3y equals -5x minus 3. And then we divide everything by -3. So this divided by -3 will be y. -5 divided by -3 is 5/3. -3 divided by -3 is +1. So we get y is 5/3 x plus 1. So I'm just going to go ahead and graph this. First I'll graph the y-intercept. If x is 0, then y is 1. You plug 0 in for x, you'll get this point right here, 0, 1. So 0, 1, I'll plot a point. Then I'm going to go 5 up and 3 over from there. So 5 up and 3 to the right. Up 1, 2, 3, 4, 5, and over 1, 2, 3. There'll be another point. And I'm going to plot that point and connect the dots to get the line. So this is the first line. Now I'm going to graph the second line by putting it in slope-intercept form. And so here it is. I'm going to solve it for y by subtracting x from both sides. I get 3y equals -x minus 15. Then I divide everything by 3. I'll get y is equal to -1/3 x minus 5. So this one, if x is 0, I'll get 0, -5 for the y-intercept. So the ordered pair for the y-intercept is 0, -5. Down here, 1, 2, 3, 4, 5. Here's 0, -5. So I'll plot a point there at 0, -5. And then from 0, -5, the slope is -1 over 3. So that's rise -1, run +3. So I'm going from here down 1, which is rise -1, and over 1, 2, 3. That's run +3. There's another point right here. And then when I connect those dots, I'll get the line in question. The point that I'm looking for, the point where the two lines intersect each other, is this point right here. So let's get the estimate here. That point is roughly, let's see, -3, -4. And we get to that point. So there we found the point of intersection for this system of equations. Does every system of equations have a solution? Here are a few graphs. So here we have the case where there's only one solution, and it's that point where the two lines cross, where two lines have different slopes. Here we have the case where they have the same slope and y-intercept, so they have infinite number of solutions because every point on the line is a solution. Those are both called consistent systems of equations. A consistent system of equations is a system of equations with at least one solution. This one has one solution exactly. This one has an infinite number of solutions. So they're both consistent systems of equations. On the other hand, if two linear equations have the same slope but different y-intercepts, then they are parallel lines and they'll never intersect each other. There will be no solution to this system of equations. This kind of system of equations is called an inconsistent system of equations. We also have a name for the case where they have the same slope and y-intercept. Because it's really only one line, what we say is that these lines are coincident lines. Coincident lines have the same slope and y-intercept. So we found one way of solving a system of linear equations, which was to graph both linear equations on the same rectangular coordinate system. Now let's take a look at two other ways. First, we'll look at substitution. To solve a system of equations by substitution, we're going to follow a certain algorithm. There's a procedure here. So here's a system of equations. Let's solve this system of equations following this procedure. First, we will solve one of the equations for one of its variables. If any variable has a coefficient of 1 or -1, it is usually the easiest to solve for. So in this case, I have a coefficient of 6, 7, -6, and 1. This first direction says if there's a coefficient of 1, it's usually easier to solve for that variable. So I'm going to solve for this x right here because it has a coefficient of 1. -1 would be my second best choice. All right, so I'm going to solve this equation for x. And to do that, all I have to do is add 6y to both sides of the equation. When I add 6y, I get x equals 6y plus 22. Next, I'm going to take this expression, 6y plus 22, and I'm going to plug it in to the other equation for the variable x. Notice x is equal to 6y plus 22. So I'm just going to take this other equation, and instead of x, I'm going to replace x with 6y plus 22. Solve for the resulting variable in the equation. I distribute, I get 36y plus 132 plus 7y is equal to -40. Then I'm going to combine like terms. 36y plus 7y makes 43y. And then I'm going to go ahead and subtract 132 from both sides. 43y is equal to -172. And then I divide both sides by 43. This is going to give me -4. Y is -4. Now I'm going to use this value for y. I'm going to substitute it in to any equation that has both x and y in it. And then I'm going to find the value of x. The equation that I'm going to use is the actual equation where x is already solved for. This one here that I solved originally. I'm just going to plug in -4 for the value of y. And then I'm going to solve this equation, or I'm going to actually simplify the right-hand side. 6 times -4 is -24. And then -24 plus 22 is equal to -2. So there I have the value of x. X is equal to -2, and y is equal to -4. So the ordered pair that is the solution to this system of equations is -2, -4. And that's how you solve a system of equations by substitution. After you finish solving it, though, you should check your solution. The other method that we use to solve a system of equations is called elimination. Let's take a look at an example of solving a system by elimination. So you'll notice here, none of these coefficients are 1 or -1. So solving for one of these variables is going to require dividing by either 3, 8, 7, or 4. But what we can do is, there's a second method called elimination that's a little bit easier in this situation. And to do elimination, the first thing we want to do is put both of the equations in standard form. In this case though, both equations are already in standard form. So next, I'm going to look at x and y. I'm going to choose which one I want to eliminate. And when I choose the one I want to eliminate, I'm going to find the least common multiple of its coefficients. So for instance, if I wanted to eliminate x, I'd find the least common multiple of 3 and 7, which is 21. If I wanted to eliminate y, I'd find the least common multiple of 8 and 4, which is 8. In this case, I think I prefer to look at the number 8 rather than 21. So I'm going to eliminate y instead of x. So what I need to do is I need to get one of these coefficients of y to be positive 8, which is lucky because one of them is already positive 8. But the other one then would need to be negative 8. I just need to figure out what I need to multiply one or both of the equations by in order to get one to be positive 8, the other one to be negative 8. In order to get the bottom one to be negative 8, I just have to multiply by negative or by positive 2. So I multiply both sides by positive 2. And then I'm just going to distribute that 2 on the left side and multiply on the right side to get 14x minus 8 is equal to negative 64. And then once I have this, I can now just add these two equations together. And once I add the two equations, I will eliminate y. So when I add the two equations, 3x plus 14x gives me 17x. The 8y minus the 8y just cancels out. That was actually the point. And the 34 minus 64 gives me negative 34. Next, I'm going to solve this equation. And when I solve this equation for the remaining variable, I'm going to get the value of x. So I divide both sides by 17, and I get x is equal to negative 2. So once I know that x is equal to negative 2, I'm going to take the value of x and I'm going to plug it into any equation that has both variables in it. So any equation that has both variables in it, I'm going to plug it in x equals negative 2. And the equation I'm choosing is 3x. I'm going to put in negative 2 for x, then plus 8y is equal to 30. I'm going to solve this. First, I'm going to do that multiplication. 3 times negative 2 is negative 6. Plus 8y equals negative 30. I add the 6 to both sides. When I add the 6 to both sides, I get 8y is equal to 36. Then I divide both sides by 8. So y is equal to 9 over 2. 4 goes into 36 9 times. 4 goes into 8 2 times. And that's my solution. The ordered pair would be negative 2 comma 9 over 2. We would just need to check the answers to make sure they actually work. Check them by plugging them in and checking to make sure they're actually the solutions. But these are the actual solutions. And this is how you solve a system of equations by elimination.